Thank you very much for giving me opportunity to give a talk in ICTS. It has been 4 years since I left ICTS. I'm very happy to be here again. So today I will talk about this question. So let's start with unitarity. Unitarity is a very important postulation in the physics. So especially in the string theories, we believe the unitarity of our theory or universe. But so often unitarity has people using unitarity, but usually they use it in different meanings. So sometimes people think unitary time evolution, or sometimes people say there is no negative norm state or some instability and so on. But sometimes they are related to each other. But and next, but recently people start talk about this non-unitarity because of first of all, there are many motivations, but my motivation in the past was like open quantum system, like in this space is also open. So when we work in the experiment, then this should be like almost, strictly speaking, it's open system. So, so this nowadays this non-unitarity time evolution or non-Hermitian Hamiltonian, they are sometimes related or not, but become very important nowadays. So in the 2D CFT, this central charge is kind of very good barometer to test to ask whether theory is unitary or non-unitary. And then we often say that CFT2 with negative central charge is non-unitary. This is if you open any CFT book, that is just the beginning of just after the Virasoro algebra, you can see this kind of statement. But let me ask this question: does negative central charge always imply non-unitarity? And this is it's closely related to this question. Is the hermiticity of the Hamiltonian always clear? We usually think it's clear, but let's see whether it's clear or not. This conference is Nonperturbative numerical approach to the quantum gravity, string, and holography. Unfortunately, today I will not talk at none of them. Sorry, I apologize about that. Today's talk is a very simple quantum mechanical system, and half of them is very easy, so that some advanced undergraduate students can understand. The rest of them, probably I don't have time to discuss in detail, but that is also very easy to PhD students. But in future, hopefully, I believe that it's related to some non-perturbative numerical calculation, and I believe that is also related to the quantum gravity and hopefully holography. So outline is just, as I mentioned, I have these two parts, but I mostly focus on this one because the essence idea is here. It's more like there is some mathematical understanding is necessary for the second part. So first one is the best place to explain this kind of phenomena. So let me focus on this. So this kind of quantum mechanics toy model starts from this project, TT-bar deformed fermionic theory. So you don't have to understand what it is, but this coming from this project, so I just briefly mentioned. So at that time, I was interested in some kind of deformation of the quantum field theory. It's not the irrelevant deformation, but it's irrelevant deformation from the IR to the UV. So this is called TT-bar deformation. Recently, it's spotlighted. But there, you deform the quantum field theory with the energy moment tensor. But if you ask how to calculate the energy moment tensor, some people say from the Lagrangian, you can using the Noether procedure and obtain the energy moment tensor. Some people say that by varying the action by using the with respect to the G mu nu, then you obtain it. So physically, you think it's the same, but here we found that it's not the same. There is some dangerous term here. It's a dangerous term is quadratic in the time derivative. This is a fermion. So usually fermion has a single linear time derivative in the side, but it has this one. So actually that has some problem. So that's why we trying to understand this phenomena, what is the problem. So we made some kind of very simple quantum mechanical model. So at that time, I didn't explain the detail about this quantum mechanical model because I focused on TT bar deformation, but now it's more important for this project. So this is usual free fermion up to here, but I add this psi quadratic in the time derivative. And it's just very easy. You can do this canonical procedure. So first you obtain this conjugate momentum by varying the with respect to the psi dot, and you obtain it. It's more like without this red term, this term will give this second class constraint, and you obtain the Dirac bracket and so on. It's just the same story. But this is more like a scalar field or bosonic, so that you can express psi dot in terms of other canonical variable. So now we don't have a constraint. So that means originally you only have psi bar because of constraint, but now you have all of them like a scalar field, or this just a boson, like a free boson. So this is a fermion doubling, but it's not the fermion doubling in the lattice, but I don't find any proper word, so I call it fermion doubling, but don't confuse with the original doubling problem. So next step is you can quantize the system. So you can express phi psi in terms of B and C, the oscillator, and theta is a kind of Bogdanov transformation. For now, you can consider as just some numerical parameter for now. It's okay. So then this kind of canonical transformation leads to this kind of the anti-commutation relation of the Fermi oscillator. So interesting part is this one. Usually you have this +1, but here it's -1. And unlike the bosonic oscillator, you cannot absorb this one -1. Like if that is a commutator, you can change exchange the role of the creation and annihilation operator, then you can also remove this -1. But this is anti-commutation relation, so that that is you cannot remove it. Then you obtain the Hamiltonian. Then let me ask, does this Hamiltonian Hermitian? So if you see here, and here this combination, and you probably answer that this is Hermitian. Now, if you have two students, then you give the two homework problem to each student. One student, you give this Hamiltonian, and calculate this matrix element. As usual in the quantum mechanical group, you ask just diagonalize. If he is a smart student, he can immediately diagonalize in front of you because this is nothing but 4x4 matrix. It's very easy. For another student, you give this Lagrangian, and you ask just evaluate this path integral, for example, in the Euclidean space. This is quadratic Gaussian integral. Everyone can do. This is a very, very easy problem. And a few lines, you can get it. Now, they give some different answer. So Bart give this answer, and Lisa give this answer. So who is correct? So one interesting part is here. This answer is real for all the real m and lambda. However, this one, for some m and lambda, it becomes complex. And they give the different result. So it's very interesting. So let me go back to this question. If you answer to this question, and if you answer the yes to this question, you believe that this part is correct. Because part result is real for all m and lambda. So if you see here, Hamiltonian, this is Hermitian for every m and lambda. Like, so you think part is correct and the Lisa is incorrect. Even though you cannot find any loop, mistake in the Lisa calculation, somehow he is correct, you might say. Yeah. Yeah.
The norm.
That's what I'm about to.
Will become.
Yeah. Okay. That's what this slide. Yes, negative norm state. That's right. That's important. So here, so because of this -1, you can first calculate this first excited state. Then you can easily conclude that by simple algebra, and this norm of the vacuum is opposite to the norm of the first excited state. That means one of them is negative norm state. So if vacuum is positive, then first excited state is negative norm state. This is similar to the Ostrowski instability for the higher spin, higher derivative theory, because this is kind of a higher derivative with respect compared to the original fermion. But then you might conclude that, that this theory is wrong because negative norm states. So we know that if there is negative norm state, something breaks down. But it's too early to conclude that. So we can define some J operator. This is a unitary and Hermitian, so that you can easily check that. This is nothing but you can imagine in the supersymmetry. You insert this -1 to the f. So this is similar to the -1 to the f, but it only have this exponentiate of the number operator of C. So then it flips the sign of the C, but it does not change this B oscillator. And one can define this J inner product by inserting J in the usual norm. Then you can easily see that in this new norm, it's norm is positive. For example, this one, you can, if you calculate, then because of the J, it changed the sign of C minus, and it flipped the sign, so that now first excited state is also positive, definitely. One of you might say it's an ad hoc, trying to change the model by introducing this kind of artificial inner product. However, we know that we always take for granted the relation between the path integral and the operator formalization. Usually in the probably undergraduate or PhD, we learn that how this path integral is related to the operator formalization by using this transition amplitude, and you insert this completeness relation. However, if you just repeat the same calculation with this system, for example, you have to insert this completeness relation, but you need this minus sign because of negative norm. Here, so here, this is identity operator is for this C dagger. Sorry, this is I didn't change the typo. This is 0. Sorry, this is not 1, 0. So there is -1, or for the using the J, you by change the plus, you can insert this J here. So that for in the completeness relation, bra has this J, you have to add this J in the completeness relation. That change a little bit the step, usually known step. And then the upshot is that this J inner product is really inconsistent with the path integral. So if you define your model with the path integral, the norm that you have to use is this J norm, not the original norm. That's the one lesson. So it's not at all. It's just if you define your theory in the path integral, then this is the correct norm, not just.
Junggi, one question on the previous slide. So here I see that you introduced anti-periodic boundary conditions for fermions.
Yeah.
So suppose you introduce periodic boundary conditions, then what would be the left-hand side?
I have to.
Do you get some version of Witten index?
I have to calculate a little bit carefully. In particular, this zero mode, I didn't consider carefully, but in the 2D case, it's more complicated 2D. So I didn't consider that.
Okay. Yeah. Thanks.
Can you use the microphone?
Can
you use the microphone?
I mean, the hermiticity refers to a norm. So I guess that with respect to this norm, H is not Hermitian. Is that correct?
You're a spoiler. Yeah, you are too fast. Okay. Yeah, I will explain soon. So that means if you just go back to this Hamiltonian, actually there are two ways to get the energy spectrum. One is using the Fock state, and using the you can calculate this matrix element by using the J norm. You can calculate also you diagonalize the matrix element, then you can obtain the energy spectrum. And you can also find this energy eigenstate by solving this equation without the matrix element. Then you will find that the result which come from the Lagrangian is correct. And something is, this is related to this previous question. So something is strange because energy can become complex. It's something very strange. Naively, it's a Hermitian, but so here we need to define the new Hermitian adjoint. Usually, if you open the linear algebra, you define the adjoint. You first define the inner product, then you define the adjoint. So because we have new adjoint, we also have the new adjoint, new J adjoint, which defined in this way. Actually, this is consistent with the usual definition of the adjoint. And the hermiticity of the operator should be defined in the with respect to this J-Hermitian adjoint. So here, now let's think of this, review the discussion. So if you see here, this term is okay, but this term with naive usual dagger, it's a Hermitian, but you have to also act the JJ here. So it flips the sign C here because it's linear in C. So it's not a Hermitian operator. It's not J-Hermitian operator because of this term. So since Hamiltonian is not J-Hermitian, it's not surprising to have a complex energy. So it's natural. Then previously here, theta is kind of Bogoliubov transformation parameter. Here I didn't explicitly write down, but this coming from the Bogoliubov transformation of the B and C oscillator. And you can ask whether you can remove some for particular theta Bogoliubov parameter. You can remove this term so that you can have explicit J-Hermitian Hamiltonian. Yeah, this is the special value. And this special value is only available for this range because of the left-hand side is tangent hyperbolic, but the right-hand side is a parabola. So for the certain value of m lambda, this range is you can have this kind of Bogoliubov transformation. So this is identical to the condition for the real energy eigenspectrum. So if there is a Bogolov transformation, you have a real energy spectrum. So here's one lesson. This is not the proof, but at least this quantum mechanical model, we can say that if there is Bogolov transformation under which Hamiltonian is J-Hermitian, one can recover the unitarity. The reason why I'm saying unitarity is this is a quadratic model, and the norm is positive, energy is real, so that it's a finite size, finite Hilbert space, so that I can conclude that this is unitarity. Now let's move to how much time I have?
We started late, so you have about 10 minutes.
Okay, yeah, I quickly go to the symplectic formula. This is a mechanism thing, but there are more interesting parts. So this is a recent work with Shinsei Ryu. And this motivation, there are many motivations. All the time, people study this model because the title is the title of the paper is also curiosity of the C equal -2 model. So I guess people start with some curiosity, but some people, for example, Gabardier and Kausher, and they are also interested in the logarithmic shift. So that Anosh asked this question about the periodic case. This is related to this logarithmic shift. Also, after that, people are also very interested in this model because the highest mean DS Shefty. So this is kind of a model that those people are they propose that this kind of symplectic fermion is due to the highest spin in the digital space. And the reason why I know this model is that my advisor, and when I joined the group, my advisor asked me to study this case. So that's why I know this kind of model. In this work, in this work and in this presentation, I don't claim the DSCFT. This is just purely quantum field theory discussion. I'm trying to avoid the holography because I don't know the detail. Because it's too, yeah, there is some kind of a lot of criticism, and I don't know the answer to that criticism. So this is just simple model, two-dimensional model with same as it's more like a scalar field, same as before, but we don't have any other term. So, and I only consider this anti-periodic case. And you can do the similar thing. Then you can quantize the theory in this way. And this n is half integer because of anti-periodic boundary condition. And in the end, you obtain this kind of commutation relation. And this is very similar to a free scalar field in the Shefty too. And you also have same problem here. And you can cure you will have this negative norm state, but you can cure this negative norm state by introducing this J operator. And then you can define J norm, J Hermitian, and so on. And then in the end, you can conclude that it has positive norm, it's quadratic, and it's a real energy eigenvalue, so that it's unitarity because it's free theory. However, we know that we can also calculate the Virasoro algebra, and we can confirm that the central charge is -2. So that by explicitly you can calculate this Virasoro generator, and then you can confirm that C is really -2. Also, there are many ways to confirm it. Now, there is a well-known theorem that CFT2 with negative central charge should have negative norm states. If you open as I said, if you open like a yellow loop, you can easily find this. It's just one line proof. Which one should I believe? This one or this one? Here I said it's a positive definite and unitary. But here another calculation C is -2. This is very simple calculation. This is also well known. So something is, there is big tension between them. So this is a counter example of this theorem. Usually, how the proof is as follows. You calculate this inner product of this L-1 to this primary states, and you change this commutator, and you obtain using the Virasoro algebra. You obtain this, and then if you see the negative for large enough, sufficiently large n, this becomes the negative. So, but here we have to using the J-Hermitian adjoint. So J-Hermitian adjoint is of Ln is not the L minus n because of this. There is a linear term in C, so it's not that relation. So if you calculate the J norm of this one, you have to calculate this one, J dagger, J adjoint, and you obtain here. Because of J, you cannot using this Virasoro algebra. So you cannot using this usual proof, so that there is no problem of there is no tension between the two. So this is a kind of counter example of the usual well-known theorem. Of course, you can ask if some of you may ask that this is unitary theory, so that if you calculate the entanglement entropy, so seemingly this is negative. Something is, but on the left-hand side, by definition, this should be positive. Also, this is something strange. This is definition. This is also well-known fact. But this kind of this negative central charge model, it found that in this paper that this entanglement entropy is not proportional to the usual central charge in the Virasoro algebra, but it's proportional to the effective central charge, where delta n is the minimum, the smallest the conformal dimension in your theory. Usually identity operator is the minimum, so that it's 0. But in this case, because of vacuum, probably I have some slide L0. Because of this term, so that now it has a positive effective central charge is 1, so that the entanglement entropy is positive. But you might say that this positive effective central charge maybe is related to unitarity, but it's not true, because this Liang model, which is a well-known non-unitary model, has also a positive effective central charge. So I'm not sure whether positive effective central charge can judge this unitarity, but this is one example that we cannot do that. So we also find that because of time limit, so I just briefly mentioned this result. So here we can also define some series of the vacuum. So we call it alpha vacua. So that it in the previous slide, in the previous Toby model, I explained that this Bogropov transformation. Here also you can define the Bogropov transformation, and you can also define this new vacuum. And then we can also calculate this correlation function with respect to this new vacuum. And the usual vacuum, with respect to just usual vacuum, this J inner product actually does not play crucial role. And even without this J norm, you can obtain the correct answer. What I mean is, in the previous paper in the literature, they obtain also correct answer, because this J act on this 0 does not change anything. So that J inner product for this correlation function doesn't matter. However, this alpha vacua is really crucial, whether you're using the J inner product or not. So this vacua is parameterized by the infinite many parameter alpha n, but for simplicity, if you choose the same value of the alpha n, you obtain this simple answer, which is same as the correlate 2-point function of the just zero vacuum. So it's independent of alpha. But you can ask what is naive correlation function. So let's say we don't know the J inner product. I just calculate the 2-point function with the naive norm. Then you obtain this one. I shortened the slide so that I need time. But yeah, here the correlation function is a linear combination of a term, which is this is usual 2-point correlation function, and this one you can consider this kind of map between the 1/g. So this is correlation function between the 1/g and 1/w, and this one is g between the 1/w and the 1/g with w. This is very similar to the a-vacua in the digital space. So in the digital space, you can think of this kind of antipodal map between the easiest way is that you consider the embedding space and the global coordinate. The antipodal map in the global ds coordinate is that just in the embedding space, it's just flip the sign, so that there is such kind of antipodal map. And the 2-point function of the massless conformally coupled scalar field in the a-vacua has this kind of result. So that there is a problem, because if you think of the quantum field theory, we accept the divergence when 2-point function is close to each other, because the operator is close to each other, you have some divergence. But in here, if you see this Fourier for this term, x and y, Fourier for the x, Fourier for this one, xa here, y, even though they are not close to each other, but it could be diverged. So something is strange. So that was very mysterious in the digital space, a-vacua in the digital space. But I think here, if you see it literally, it's very similar. The naive norm in this in black fermion is related to this 2-point function in the a-vacua. So we believe that there is some kind of we need some more understanding of the a-vacua. Unfortunately, we cannot find yet of the resolution in this the correlation function in the a-vacua of the digital space. But I believe that this kind of our model will help to understand the quantum field theory in the digital space. So the answer to this question is no. And this is hermiticity is you always have to be careful. Thank you very much for your attention.
Any questions? I have one. I mean, sometimes the option that you have is between stability of the vacuum and how you call it, or negative norm states. So sometimes the resolution is that the vacuum is not stable and you can lower the energy.
Yeah.
But this is different, right?
Yeah. So that happened in the bosonic system, higher derivative bosonic system, like Ostra-Zagorski. And then you have to, by there, you can have instability, or you have a negative, you can have a negative norm state, but you by exchanging the creation and annihilation, then you kind of avoid the negative norm state. But at the same time, the energy will be not bounded below. That is a really big problem. But here, no, it's something is different. Because first reason is it's fermion, so that this exchange of the creation annihilation does not have this problem because anti-commutation. And also for even quantum mechanical system, it's finite, right? So it's not problem of the bounded below problem. So
okay. Anyone else? Masanori, do you have a microphone nearby?
Yeah. I had a question regarding how do you exactly impose constraints when you have changed the norm and gone to this J norm definition? Because usually in the Dirac procedure, when you have a constraint theory, you can just impose it on the kets, and the natural bra that comes from the kets automatically follows through with the constraint imposition through the Dirac procedure. But do you have to be careful here regarding that?
First of all, here we don't have a constraint because original fermion has a constraint. But now, because of the Fourier Toy model, because like it's a scalar field, we don't, unless we imposing Lagrangian, some influence Lagrangian multiplier, we don't have any constraint. Also here, we don't have such a constraint.
Yeah, I'm talking about improving the model and going to some like gauge constraints or some additional constraints if there were in the theory.
Yeah,
I had to do something like this to improve the norm and like modify the norm into a J norm.
That I don't know because first of all, even this, I only talk about the quadratic theory. I don't know the interacting case nor this gauge constraint system. It will be very easy, it would be very interesting problem for future. So there is like a Leclerc also trying to understand this interacting case, but one need to carefully analyze such kind of case. Question. So answer is I don't know.
I see. Thank you.
No, are there any more questions? You can go ahead. There's a microphone next to you. It has a latency. It takes a while.
Because of this J norm thing, you should not write CC dagger somehow, because I think C dagger is not the Hermitian of C, right?
No,
That's
so
the first thing.
So here,
When you write CC dagger, I mean, implicitly you're saying it's the Hermitian, but it's not really so because of the J norm.
yeah.
Right?
So
Yeah, that's what it's just a comment. I think it's.
yeah. So this J usually people trying to avoid that case, like instead of dagger, people using bar or something.
Right,
But
right.
yeah. So
right.
yeah, this is just so
Because
that's
if you write it with the real dagger,
yeah.
then that will show up nicely, no?
Yeah.
So I think you can just change, put bar and then change
Yeah,
that to
that's
dagger,
right,
and
that's
everything
one way,
looks
yeah.
nice.
Yeah, so that's why here I trying to distinguish it dagger and the dagger with the J.
Yeah,
So
yeah,
that
okay.
is one way.
No,
So.
thank you. Nice talk.
Okay, so let's thank Junggi again.